Here's what we're going to do today. What is the idea behind a simplex method? We start from a feasible solution to the linear program that we would like to solve. And then we do row operations to get to other feasible solutions that give us better and better and better objective values. But the important point of the statement is that when we solve a linear program through the simplex method, we start from an initial feasible solution. We start from a feasible solution to the linear program that we would like to solve. And we do row operations to get to other feasible solutions that give us better and better and better objective values. For the linear programs that we looked at so far, finding a feasible solution to get the simplex method started, finding an initial feasible solution for the simplex method to get started with, was not an issue. But if the linear program that we're dealing with is very complicated, it's not that easy to find an initial feasible solution for the simplex method to get started with. So in this lecture, we're going to see a systematic way for us to find an initial feasible solution for the simplex method to get started with, so that we can apply the simplex method starting from that feasible solution to get to even better objective values and finally to the optimal solution. So then how can I find a feasible solution to my linear program so that I can start the simplex method with that feasible solution and hopefully get to better and better and better and better feasible solutions that give us better and better and better objective values. Okay, good. So let's start with a case where it was easy to find initial feasible solutions. And let's also look at a case where it's difficult to find an initial feasible solution to the linear program so that we can contrast these two situations a little bit carefully. So let's say that we have a linear program that looks like this. Share my screen. So let's say that we have a linear program. The objective function is 3x1 plus 2x2, subject to x1 plus 2x2 is less than or equal to 12. 2x1 plus x2 is less than or equal to 11. And x1 plus x2 is less than or equal to 7. My decision variables are non-negative. Okay. So if you wanted to solve this linear program through the simplex method, what did we do? We first turned all of our inequality constraints into equality constraints by using the slack variables. Let's do that. Keep the objective function the same. Put the slack variable for the first constraint, so stuff the left-hand side of the first constraint with a sock. W1 is my sock. So that this becomes an equality constraint. Stuff the left-hand side of the second constraint with another slack. Stuff the left-hand side of the third constraint with another slack. And all my decision variables and all my slacks are non-negative. So in my simplex algorithm, in my simplex method, I work with this linear program that has the equality constraints. So in the first iteration of the simplex method, what did we do? We wrote down our system of linear equations. Oh. This is the system of equations that my simplex method started with, and then treat a solution to the system of linear equations so that we could get the simplex method, started with that solution. We identify 3 decision variables, each lying in a different constraint row with a coefficient of 1. Then the solution we read from this system of linear equations is W1 is 12, W2 equals 11, W3 equals 7, x1, x2 is equal to 0. If x1, x2 are 0, z has to be equal to 0. Good. So this is how we so far started our simplex method. This was the initial solution that we started with. And from this point on, we applied iterations of the simplex method to get to better and better and better feasible solutions. And is this solution feasible to the linear program that we would like to solve? Let's check against the version that has got inequality constraints. x1 and x2 are 0. 0 plus 0 is less than or equal to 12. This is satisfied. 0 plus 0 is less than or equal to 11. 0 plus 0 is less than or equal to 7. And my 0 is greater than or equal to 0. 0 is greater than or equal to 0. So this solution is feasible to my linear program. And again, if you want to check the version with the equality constraints. X1 and X2 are 0, W1 is 12. So 12 equals 12. X1 and X2 are 0, W1 is equal to 11. 11 equals 11. X1 and X2 are 0, W3 is 7. 7 equals 7. And all the X and Ws are non-negative. So this solution is feasible to the linear program that I would like to solve, whichever version of the linear program we're looking at. Okay. So then simplex method, what the simplex method did is it started from this initial feasible solution. It started from this feasible solution, and we applied row operations to get to better and better and better feasible solutions. Okay, so let's say this solution is feasible to the LP we want to solve. Good. So this is business as usual. This is what we've seen in the last two lectures. This is how we initialize the simplex method. It was easy to get an initial feasible solution to the linear program. And from that feasible solution, we did row operations to get to better and better feasible solutions. Let's look at another, a little bit more interesting, a little bit more complicated linear program. Let's say that our linear program looks like this. Maximize x1 plus x2, subject to an equality constraint that looks like this, subject to another inequality constraint, subject to yet another inequality constraints, and x1 and x2 are non-negative. Let's apply the same recipe to get our simplex method started. What do? We first express all of the constraints as equality constraints by using slack variables. Let's apply the same recipe. So stuff the left-hand side of this first constraint by the slack variable W1, make it an equality. Stuff the left-hand side of the second constraint by the slack variable W2, make it an equality, Stuff the left-hand side of the third constraint by the slack variable W3, make it an equality. And all of our decision variables, all the slacks are non-negative. Great, so now let's write down the system of linear equations that our simplex method is going to start with. Objective function rho. First constraint, no. Second constraint, rho. Third constraint. Do we have three decision variables such that each one of these decision variables appears in a different constraint row with a coefficient of 1? Nowhere else. Yes, those are W1, W2, W3. Let's read that. W1 equals minus 28. W2 equals 20. W3 equals minus 24. In this case, X1, these are going to be by non-basic variables. X1 and X2 are going to be 0. If X1 and X2 are 0, Z is going to be 0. Okay. So the question is this solution that we quick read from this initial system of equations feasible to the linear program that we would like to solve? Let's check it. Let's check against the linear program with the inequality constraint. X1 and X2 are 0. 0 plus 0, the left-hand side is 0. Is 0 less than or equal to minus 28? No. This solution violates the first constraint, so this solution is not feasible to the linear program that we would like to solve. Okay? And likewise, if you check the version with the equality constraints, x1, x2 are 0, w1 is minus 28, so it's minus 28. x2 is 0, w2 is 20, so the left-hand side is 20, right-hand side is 20, okay. x1 and x2 are 0, w3 is minus 24, minus 24 equals minus 24. So these guys are satisfied, but my w's are not non-negative. The first W1 and the W3 are negative, so I violate non-negativity constraint. So whichever you look at, whenever you look at, this solution is not feasible to the linear program that we would like to solve. So then, when I initialize my simplex method as business as usual, in the way that we've seen in the past two lectures, then this solution is not feasible to the linear program that we would like to solve. So then simplex method cannot start from this feasible solution and get to other feasible solutions that give us better and better objective values. And in fact, we don't even know if there exist feasible solutions to this linear program. Maybe there is no x1, x2 pair that satisfies all of the constraints in my linear program. Okay, so that is the question that we're going to resolve today. So how can I find a feasible solution to this linear program in a systematic fashion so that I can start the simplex method from that feasible solution, and then do the iterations of the simplex method to get to better and better feasible solutions that give us better and better objective values. Okay, so today our job is, how can I come up with a systematic approach to find a feasible solution to a linear program that you give me, so that again I can use that feasible solution as the initial feasible solution in my simplex method, and then do the iterations of the simplex method to get to better and better feasible solutions. Okay, good. So this solution is not feasible to the LP we want to solve. In fact, we don't even know. In fact, we don't even know if this linear program as a feasible solution, right? Let's say, so the simplex method cannot start from this solution. And the question is, how can we systematically find a feasible solution to the LP we want to solve? Good. And it turns out that we're going to see that to find a feasible solution to an LP that we want to solve, we can solve yet another LP. Okay, so that's what we're going to do. Find a feasible solution to the LP we want to solve. It turns out we can solve another LP. It turns out we can solve another LP. Let's see what that LP looks like. So here's the linear program that I would like to solve. Let me put it in the corner here. Here's the linear program that I would like to solve. And I want a feasible solution to this linear program so that I can get my simplex method, start from that feasible solution, and then apply the iterations of the simplex method to get to better and better feasible solutions. Okay, so my goal is to find a feasible solution to this linear program. And it turns out to find a feasible solution to this linear program, I can solve yet another linear program. And let me show you what that linear program looks like. Let's write down the constraints of our linear program. Okay, so now we're going to construct a linear program that we can use to find a feasible solution to this linear program. To construct that linear program, we copy the constraints of my original linear program as they are. So now let me add a decision variable, u, to the right-hand side of each one of these constraints, okay? And use a non-negative decision variable. And in the objective function, let me minimize the decision variable, u. Okay? This linear program is called the phase-1 linear program. We call this as the phase-1 linear program because this is the linear program that we solve to find a feasible solution to the linear program that we're eventually interested in solving. So this linear program is only going to find us a feasible solution to the linear program that we would like to solve. Later on, starting from that feasible solution in phase 2, we're going to apply the simplex method to find the optimal solution. But this linear program is only going to be used to find a feasible solution to this linear program that we would like to solve. So this linear program is called the phase-1 linear program. Phase-1 linear program. And this u decision variable that we added over here also has a name. It's called the artificial variable. Not terribly important. Okay. So now let's think about how this linear program would allow us to find a feasible solution to this original linear program that we would like to solve. The first observation is that the phase-1 linear program is always feasible. The phase-1 linear program is always feasible. To see that, here's a feasible solution to my phase-1 linear program. Set u to be 28. Set all the x's to be 0. If u is 28, if u is 28, if u is 28, then the right-hand side of this constraint is going to be minus 28 plus 28, 0. 20 plus 28 is 48. Minus 24 plus 28 is 4. Those are the right-hand side. And set x is to be 0. 0 is less than or equal to 4. 0 is less than or equal to 48. 0 is less than or equal to 4. So the phase one linear program is always feasible. Set u to be the most negative right-hand side and set all the x's to be 0. That's going to be a feasible solution to phase one linear program. So the feasibility is not a question for the phase one linear program. So let's make that observation. Phase one linear program is always feasible. Set u to be 0 and x1 0 and x2 0. I'm sorry, set u to be, what did we say? Set u to be 28. Set u to be 28. Negative of the most negative right-hand side, x1 0, x2 0. If u is 28, then the right-hand side of this full thing is going to be 0. The right-hand side of this full thing is going to be 48. The right-hand side of this full thing is going to be 4 if u is 28. And if x's are all 0, 0 is less than or equal to 0, 0 is less than or equal to 48, 0 is less than or equal to 4. So this solution would be feasible. So phase one linear program is always feasible. There is no question of the feasibility of the phase one linear program. There's always a feasible solution. On the other hand, let's look at what we're doing in phase one linear program. In the objective function of the phase one linear program, I'm pushing u as low as possible. And u is non-negative. U is greater than or equal to 0. In the objective function of the phase one linear program, I'm pushing u as low as possible, and u is greater than or equal to 0. So if at all possible, in the optimal solution to phase one linear program, I want to push u all the way down to 0. If at the optimal solution to the phase one linear program, if I'm able to push u all the way down to the 0, if u's are all equal to 0, then the values of the x decision variables at the optimal solution to phase one linear program, u's are all zeros, is going to be a feasible solution to the linear program that I would like to solve. It's going to be the same constraint. Good. So I solved the phase one linear program, and in the objective function of the phase one linear program, I'm pushing u as low as possible, and u is greater than or equal to 0. So if at all possible, I'm going to push u all the way down to 0. If at the optimal solution to phase one linear program, I'm able to push u all the way down to the 0, it means that u's are all 0, so there's no u anymore. Then the values of the x variables at the optimal solution to phase one linear program are going to satisfy the constraints of the original linear program that I would like to solve. So that's going to be a feasible solution to the original linear program that I would like to solve. If on the other hand, if the optimal solution to phase one linear program, u is strictly greater than 0. So no matter what I do, I couldn't push u all the way down to 0 and find the corresponding x's that satisfy all of these constraints. If at the optimal solution to the phase one linear program, if the value of u is strictly greater than 0, then I couldn't push u all the way to 0 while finding the feasible values of the x's that satisfy these constraints. Then that means that the original linear program that I would like to solve is infeasible. Okay, so that's how we're going to find an initial feasible solution to the original linear program that I would like to solve, and also how to detect whether the original linear program that I would like to solve is even feasible. Okay. So let's write it as if the optimal solution x1, x2, and u star of the phase 1 LP, if the optimal solution x1, x2, x star, x1, x2, u star of the phase 1 LP has u star equals 0, and if we have u star equals 0 at the optimal solution to the phase 1 linear program, then what do we have? This optimal solution has to satisfy all of the constraints in the phase 1 linear program. It's going to be x1 minus 3x2 star has to be less than or equal to 28 plus u star. X2 star has to be less than or equal to 20 plus u star. Minus x1 star minus x2 star has to be less than or equal to minus 24 plus u star. And x1 star, x2 star has to be non-negative. If at the optimal solution of my phase 1 linear program, we have u star equals 0. So that's a 0, that's a 0, that's a 0, that's a 0. These are zeros. Then the values of x1, x2 star satisfies all of the constraints in the original linear program that I would like to solve. Then x1, x2 star is a feasible solution to the original linear program that I would like to solve. On the other hand, if the optimal solution x1, x2, x2 star, x1, x2, u2, x1, x2, u star of the phase one linear program has u strictly greater than 0, then there's no way I could push u all the way down to 0 while finding the corresponding values of the x's that satisfies these constraints. That means that the original LP that I would like to solve is infeasible. If the optimal solution of the phase 1 LP has u star strictly greater than 0, then the original LP we would like to solve is infeasible. So then that is our tool. Our tool is the phase 1 linear program. If you want to find an feasible solution to the linear program that we would like to solve the phase 1 linear program. If at the optimal solution to the phase 1 linear program, u star is equal to 0, then the corresponding values of the x variables is going to be a feasible solution to the original linear program that we would like to solve. And if at the optimal solution to the phase 1 linear program, u star is stuck at a value that's strictly greater than 0, then there is no feasible solution to the original linear program that we would like to solve. So then to find a feasible solution to the original linear program that we would like to solve, let's go ahead and solve the phase 1 linear program. So let's write down the system of linear equations that we need to write to solve the phase 1 linear program. Here's my objective function row. Let me write the constraint rows first. Let's go ahead and plug in the Slack, put in the Slack videos because now we're pretty comfortable with that already. Stuff in the Slack variable W1 here. And throw in the u decision variable to the left-hand side. So all of my decision variables are on the left-hand side. So minus u equals minus 28. So this is my first constraint. This is my first constraint written with the Slack variable and u thrown to the other side. Let's write down the second constraint, w2, x2 plus the Slack variable w2 for the second constraint and move u to the other side equals 20. Let's write down the third constraint, minus x1 minus x2 plus w3 equals minus 24 plus u. Put u to the other side. That becomes equals minus 24. That is the third constraint. And my u, my objective function, u is equal to z. Okay. This is the system of linear equations that I start with if I'm trying to solve the phase 1 linear program. Okay. Are there 3 decision variables, each appearing in a different constraint row with a coefficient of 1 and nowhere else? Yes, there are. What are they? W1, W2, W3. So now what is the solution we read? W1 is minus 28, W2 is 20, W3 is equal to minus 24. And if you set the W's like this, x1, x2, and u are going to be 0. If u is 0, z is going to be 0 as well. Okay, so this is the system of linear equations that I use to solve my phase 1 linear program. Let's see if this solution is feasible to my phase 1 linear program. X's are zeros, u's are also zeros. X's are zeros, u's is also 0. 0 plus 0, that's a 0 on the left-hand side. Minus 28 plus 0, that's a minus 28 on the right-hand side. Is 0 less than or equal to minus 28? No. So this solution is not feasible to my phase 1 linear program as well. So it looks like I cannot even get started my simplex method to solve the phase 1 linear program either, right? This solution is not feasible to the phase 1 linear program. x1, x2, and u's are 0. x1 is 0, x2 is 0. That's a 0 here. U is also a 0. That's a 0 here. 0, is it less than or equal to minus 28? It's not. So this solution is not feasible to my phase 1 linear program. So now I'm panicking. I can't even find a feasible solution to get simplex method started to solve the phase 1 linear program. So I'm panicking a little bit, but we're going to fix this. this solution is not feasible to phase one linear program. So now we're really worried something bad could be happening. So there's my skull and crossbones. But it turns out we can do one trick row operations to quickly get a feasible solution to the system of linear equations. We can do one trick row operation. One trick row operation, and that trick row operation is that you take the constraint with the most negative right-hand side, minus 28. You take the constraint with the most negative right-hand side, minus 28. Add that constraint to the objective function, subtract that constraint from each one of these constraint rows. If you do that one trick row operation, you immediately get a feasible solution to your phase one linear program. And that's a trick. Like somebody shows you that trick, you learn the trick, and you keep that trick in mind. This is not something that you could figure out on your own. That's a trick row operation, okay? So do a special row operation to get a feasible solution to the phase one LP. Take the constraint with the most negative right-hand side. Add it to the objective function row. And subtract from all other constraint rows. So this is a trick. Again, it's not something you figure out on your own. Somebody tells you how to do this. It's a trick, and this is why you're sitting in this course. Let's do those row operations and see what we get. Take the first row, the one with the most negative right-hand side, add it to the objective function row. So in that case, what do we get? X1 minus 3x2 plus W1 minus U and plus U are going to cancel. And on the right-hand side, we get Z minus 28. And subtract this row from every other row. So multiply the first constraint by -1, add it to the second constraint row. X1 times -1 is minus X1, add it over here, minus X1. X2 times minus 3x2 times -1 is 3x2, add it over here, 4x2. W1 times -1 is minus W1, no W1, minus W1. No W2 plus another W2, W2. No W3, no W3. Minus U times -1 is plus U, another -2, U disappears. And on the right-hand side, minus 28 times -1 is plus 28, another 20 on top of that, 48. Likewise, multiply the first constraint by -1, add it to the third constraint row. X1 times -1 is minus X1, another minus X1, minus 2X1. Minus 3X2 times -1 is 3X2, minus 10X2, 2x2. W1 times -1 is minus W1, plus 0 W1, minus W1. No W, no W2, no W2. 0 W3 times -1 is 0 W3, plus another W3, W3. Minus U times -1 is plus U, another minus U, U disappears. Minus 28 times -1 is plus 28. 28 minus 24, that's a 4 on the right-hand side. Great. And I'm going to want to, in a moment, identify U as a basic variable. So let's multiply this row all across by -1. Minus X1 plus 3X2 minus U minus W1 plus U equals 28. Okay. Good. In this system of equations, do we have three decision variables such that each appears in a different constraint row with a coefficient of 1? Yes, my basic variables are U, W2, and W3. So then we read the solution. U is equal to 28, WT equals 48, and W3 equals 4. X1, X2, and W1 are 0. And Z is equal to 28. Is this solution feasible to the phase 1 linear program that we would like to solve? Is this solution feasible to the phase 1 linear program? U is 28, X1 and X2 are 0. U is 28, X1 and X2 is 0. 0 plus 0 is 0, minus 28 plus 28 is 0. 0 is less than or equal to 0. I'm in good shape. X2 is 0, U is 28. This is 48 here. This is 0 on the left-hand side. 0 is less than or equal to 48. I'm in good shape. 0, 0, 0 on the left-hand side. Minus 24 plus 28. U is 28. 4 on the right-hand side. 0 is less than or equal to 4. I'm in good shape. And U is 28. My x's are 0. X's are non-negative. U is non-negative. I'm in good shape. So this solution is feasible to the phase 1 linear program. So then I can apply the simplex method starting from this feasible solution to get to better and better and better feasible solutions. So this special trick row operation allows me to get a initial feasible solution for the phase 1 linear program so that I can start the simplex method for the phase 1 linear program with this feasible solution. Great. So then from this feasible solution, I want to try to get to better and better feasible solutions. Remember, in the objective function of the phase 1 linear program, I'm minimizing the objective function. This is a minimization problem. I'm trying to get the objective function as small as possible. Let's scan the objective function row. I want to get to a better objective value. For each unit of increase in x1, the objective function goes up by 1 unit, and I'm trying to make the objective function smaller. So it's not a good idea to increase x1 if I want to make the objective function smaller. I'm minimizing the objective function. For each unit of increase in x2, the objective function goes down by 3 units. If I'm minimizing the objective function in the phase 1 linear program, so increasing x2 is a good idea. For each unit of increase in W1, the objective function goes up by one unit. So it's not a good idea to increase W1 either. So we're going to increase X1. I'm sorry, we're going to increase X2. If I increase X2, for each unit of increase in X2, the objective function is going to go down by 3 units, and I'm trying to minimize the objective function. So it's a good idea to increase X2. Okay. So now let's ask ourselves how much we can increase X2 before we get in trouble. From the first constraint row, as I increase X2, I'm going to eat up the increase X2 by playing around with U. Right now, X2 is equal to 0, U is equal to 28. U is equal to 28. If I said X2 to be equal to 1, U is going to go down to 25, so that they add up to 28. So what is the largest X2 can go before U turns negative? It is 28 over 3. So from first constraint, can increase X2 up to 28 over 3 before U turns negative. From the second constraint, what is the largest that I can increase X2 up to before W2 turns negative? It is 48 over 4. That's a 12. When X2 is equal to 12, this is going to be 48. So then W2 has to turn to 0 at that point. Can increase X2 up to 48 divided by 12. 48 divided by 12, that's a 4 before W2 turns negative. And lastly, from the third constraint, how much can I increase X2 before W3 turns negative? 4 divided by 2, that's a 2. W3. So from the first constraint, I can increase X2 all the way to 28 over 3. Second constraint, I can increase X2 all the way to 4. From the third constraint, I can increase X2 all the way to 2 before I get in trouble. So the best I can increase X2 before I get in trouble is 2. So in this case, the new value of x2 is determined by the third constraint row. We're going to do row operations such that x2 appears only in the third constraint row. We're going to do row operations so that x2 appears only in the third constraint row. Let's do those row operations. I want x2 to appear only in the third constraint row. To get rid of x2 in the objective function row, multiply the third constraint row by 3/2 and add it to the objective function row. I want x2 to disappear from the first constraint row, multiply the third constraint row by minus 3/2 added to the first constraint row. And I want x2 to disappear from the second constraint row, multiply the third constraint row by minus 2 added into the second constraint row. Let's do those row operations. Let's take care of the objective function row. Minus 2x1 times 3/2 minus 2x1 times 3/2, that is going to give us minus 3x1 plus another x1, that is going to give us minus 2x1. Let's keep going. 2x2 times 3/2, 3x2, minus another 3x2, x2 goes away, that's what we're trying to do. Minus w1 times 3/2, minus 3/2 w1, plus another w1, minus 3/2 plus 1, that is going to give us minus 1/2 w1. No w2, no w2, so we're going to have no w2. w3 times 3/2, 3/2 w3 plus 0 w3, that's going to be 3/2 w3. No u, no u, we're not going to have any use here anymore. We're not going to have any use. And lastly, let's take care of the right-hand side, z. 4 times 3/2, that is a 6. There's a minus 28 here. That is going to be minus 28. 6 minus 28, that is minus 22. Good. Let's take care of the first constraint row. Multiply the third constraint row by minus 3/2, add it to the first constraint row. Minus 2x1 times minus 3/2, that is going to give us plus 3x1. Another minus x1, that is going to be 2x1. 2x2 times minus 3/2, that is going to be minus 3x2, plus another 3x2, 0x2, that's what I want, x1, x2 to disappear. Minus w1 times 3/2, that is going to be 3/2 w1, minus another w1, 3/2 minus 1, that is going to give me plus 1/2 w1. No w3, I'm sorry, no w2, no w2, so no w2 here. w3 times minus 3/2 plus 0 w3 minus 3/2 w3. 0u times minus 3/2 is 0u plus another u on top of that. We're going to have u here. That is equal to 4 times minus 3/2, it's going to give us minus 12/2, that's a minus 6, plus another 28, that is going to be 22. Good. Let's take care of the second constraint row. Multiply the third constraint row by minus 2, add it to the second constraint row. Minus 2x1 times minus 2 is 4x1. Another minus x1, that's going to give us 3x1. 2 times x2 times minus 2 is minus 4x2, plus another 4x2, 0x2, x2 goes away, that's what we want. Minus w1 times minus 2, it's 2w1, minus another w1, plus w1. 0 w2 times minus 2 is 0 w2, plus another w2, w2. w3 times minus 2 is minus 2 w3, plus another 0 w3, minus 2 w3. No u, no u, no u here. 2 times minus 2 is, I'm sorry, 4 times minus 2 is minus 8, plus another 48 on that, 40. And lastly, I want x2 to appear. I want x2 to appear in the third constraint with a coefficient of 1. Multiply everything across by 1/2. So we get minus x1 plus x2 minus 1/2 w1 plus 1/2 w3 is equal to 2. Okay. So this is the next system of equations we reach. Good. Good. Do we have three decision variables, each appearing in a different constraint or with a coefficient of 1? Yes. So the solution that we read from the system is u is equal to 22, my basic variables. W2 is equal to 40, and x2 is equal to 2, x1, w1, w3 are all zeros. If x1, w1, w3 are zeros, z should be equal to 22. In the previous iteration, our objective function was 28. Now we decrease the objective function to 22. Remember, we're minimizing the objective function, so we're making progress. Okay. The question is, we're minimizing the objective function. The question is, are we at the optimal solution? Is there any decision variable that we can increase to make the objective value better? Is there any decision variable that we can increase to decrease the objective value even further? For each unit of increase in x1, the objective function goes down by -2. So good, I can increase x1 to make my objective value better. For each unit of increase in w1, the objective function goes down by -1/2. Increasing w1 also makes the objective value better, smaller. But increasing w3, for each of increasing w3, the objective function goes up by 3/4 or 2. So increasing w3 is not a good idea. So we're either going to increase the x1 or w1, but I get a bigger bang for my buck. Each unit of increase in w1 decrease the objective value by -2 units. Let's go ahead and increase x1. Increasing x1 gives me a bigger bang for my buck. For each unit of increase in x1, the objective function goes down by 2 units as opposed to 1/2 units. So let's go ahead and increase x1. So if I increase x1, how much can I increase x1 before I get in trouble? Let's look at constraint 1. As I increase x1, I'm going to eat up the increase x1 by playing around with u. Right now, x1 is equal to 0, u is equal to 22. Okay. If I increase x1 all the way to 11, this is going to be 22, u is going to snap to 0, and that is the largest x1 can go. So from the first constraint, and increase x1 up to, let's say 22 divided by 2, which is an 11, before u turns negative. Let's look at constraint 2. From second constraint, as I increase x1, x1 is 0 right now, w2 is 40. As I increase x1, I'm going to make up for the increase in x1 by playing around with w2. Right now, this is 0, this is 40. If I increase x1 all the way to 40 divided by 3, this is going to be 40, then w2 has to turn to 0, and that is the largest I can increase x1 before w2 turns negative. And what's happening in constraint 3? I'm increasing x1, we're increasing x1, we're increasing x1. So right now, x1 is 0, x2 is 2. As I increase x1, we're going to make up for the increase in x1 by playing around with x2. Right now, this is 0, x2 is 2. If I increase x1 to 10, this is -10, to make sure that they add up to 12, x1, x2 is going to go up to 12, so that -10 plus 12 is going to be 2. If I increase x1 to 50, -50, x2 has to be equal to 52, so that -50 plus 52, they add up to 2. So if I increase x1 to 1000, -1000, x2 has to be 1002, so that they add up to 2. So since x1 appears in the third constraint row with a negative coefficient, from the perspective of the third constraint, we can increase x1 as much as we want. We can increase x1 as much as we want without x2 turning negative. Okay, so the first constraint says you can increase x1 before we get in trouble. The second constraint says we can increase x1 to 40/3 before we get in trouble. The third constraint says you can increase x1 as much as you want, you're not going to get in trouble. Which one is the binding one? 40/3 is like 13 point something something. So 11 is the binding one, so we're going to increase x1 up to 11. Increasing x1 to the minimum of 11 and 40/3. The minimum occurs at 11. So that means that the new value of x1 is going to be determined by the first constraint, which means that we're going to do row operations such that x1 appears only in the first constraint. do row operations such that x1 appears only in constraint 1. So I want x1 to appear only in constraint 1. So if I want x1 to disappear from the objective function row, take the first constraint row, just add it to the objective function row. That's going to make x1 disappear from the objective function row. If I want x1 to disappear from the second constraint row, take the first constraint, multiply it by -3/2, add it to the second constraint row, then x1 is going to disappear from the second constraint row. And if I want x1 to disappear from the third constraint row, take the first constraint row, multiply it by 1/2, add it to the last constraint row, then x1 is going to disappear from the last constraint row. So then let's do those row operations. Add the first constraint row to the objective function row to make x1 disappear. This plus this is 0x1, that's what I wanted. 0x2, 0x2, 0x2. Add this thing to this, that is going to be equal to -1/2 W1, -1/2 W1, that's a 0 W1. No W2, no W2, no W2. -3/2 W3 plus 3/2 W3, W3 disappears. U is added to the objective function. Again, take this row, add it over here. If you do that on the right-hand side, we have z -22 plus 2, that's a 0 as well. That's what we have in the objective function row. Let's take care of the second constraint row. Multiply the first constraint row by -3/2, add it to the second constraint row. 2x1 times -3/2 is -3x1 plus 3x1, that's a 0. x1 goes away, that's what I want. I want x1 to disappear from the second constraint row. 0x2 times -3/2, 0x2 plus another 0x2, 0x2 here. 1/2 W1 -3/2, that is going to give me -3/4 W1. Another W1 -3/4 W1 plus another W1, that's going to give us 1/4 W1. Let's keep going and finish the row operations. No W2, 0 W2 times -3/2, that's 0 W2 plus another W2. We have W2 here. -3/2 W3 times -3/3, that is going to be 9/4. 9/4 minus 2. 9/4 minus 2. That's 9/4 minus 8/4. That is 1/4. U times -3/2 is -3/2u plus another 0u. That is just -3/2u. And on the right-hand side, 22 times -3/2 is -33 plus another 40. That's the 7 on the right-hand side. Let's take care of the third constraint row. Multiply the first constraint row by 1/2, add it to the third constraint row. 2 times x1 times 1/2 is x1 minus another x1, x1 goes away. 0x2 times 1/2 is 0x2 plus another x2, we got x2 here. 1/2 W1 times 1/2, that is 1/4 W1 minus another 1/2, 1/4 minus 1/2, that is going to give us -1/4 W1. No W2 plus no W2, no W2. -3/2 W3 times 1/2, that is -3/4, plus another 1/2 W3, -3/4, plus another 1/2 B set, -3/4 plus 2/4, that is -1/4 W3. And lastly, U times 1/2 is 1/2 U plus 0U, that is 1/2 U. And on the right-hand side, 12 times 1/2 is, I'm sorry, 22 times 1/2 is 11 plus another 3. 22 times 1/2 is 11 plus another 2, 30. And I want x1 to appear on this row with a coefficient of 1. So let's multiply this constraint by 1/2 across. That is an x1, 1/4 W1 minus 3/2 W3. I'm sorry, we're multiplying across by 1/2. x1, 1/4 W1, 3/4 W3, and 1/2 U equals 11. Good. This is the system of equations we reach. What are my basic variables? Those are my basic variables. So then what is the solution we read? X1 equals 11. X2 equals 7. Let's go in order like we always do. X1 equals 11, W2 equals 7. X2 equals 30. And W1, W3, and U are 0. If U is equal to 0, Z is equal to 0. Good. This is the solution that we obtain in the current iteration. Have we reached the optimal solution to the phase-1 linear program? Are there any decision variables that we can increase to make the objective value smaller? No. If you increase U, the objective function is going to go up. For each unit of increase in U, the objective function is going to go up. So there is no decision variable that we can increase to make the objective value go down. As a result, this is the optimal solution to the phase-1 linear program. The optimal solution to phase-1 linear program is let's say X1, X2, W1, W2, W3, and U. X1 is what? 11. X2 is what? 13. W1 is 0. W2 is 7. W3 is 0. And U is 0. Okay. Let's put the star. Do we have U star equals 0 at the optimal solution to phase-1 linear program? Yes. Then the values of these X1, X2 variables has to be feasible to the original linear program that we would like to solve. We have U star equals 0 at the optimal solution to phase-1 LP. Thus, X1 star, X2 star equals 11 and 13 is, let's say, must be, no big deal, must be feasible to the original LP we want to solve. Let's check if X1 equals 11, X2 equals 13 is feasible to the original linear program that we would like to solve. Here is the original linear program that we would like to solve. X1 is 11, X2 is 13. 11 minus 3 times 13, 11 minus 39 is minus 28. 11 minus 39 is minus 28. Minus 28 is less than or equal to minus 28. The first constraint is satisfied. X2 is 13. 13 is less than or equal to 20. Second constraint is satisfied. This is 11. This is 13. Minus 11 minus 13, that is minus 24. Minus 24 is less than or equal to minus 24. The third constraint is satisfied. X1 is non-negative. X2 is non-negative. This is indeed a feasible solution. So now what we have here is that X1, X2, 11, 13 is a feasible solution to the linear program that we would like to solve. It's a feasible solution to the linear program that we would like to solve. Okay, so now I have a feasible solution to this linear program that we would like to solve. It doesn't mean that the solution is optimal to this linear program. What we're going to do next is, starting from this feasible solution, we're going to apply the iterations of the simplex method on the linear program that we would like to solve to get to the optimal solution. Okay, and that is going to be our job in the next lecture. Okay, so in this lecture, we use the phase-1 linear program to find a feasible solution to this linear program. And our job in the next lecture is going to be, by starting from this feasible solution, we're going to apply iterations of the simplex method on the original linear program that we would like to solve to get to the optimal solution to this linear program. That's going to be our job in the next lecture. So what we did today is we came up with this cute phase-1 linear program that allow us to get a feasible solution to a linear program that we would like to solve. You construct the phase-1 linear program. You solve the phase-1 linear program. If at the optimal solution to the phase-1 linear program, u variable takes exactly value equals 0, then the values of the x variables are going to be a feasible solution to the original linear program that I would like to solve. And if I solve the phase-1 linear program at the optimal solution to phase-1 linear program, if u decision variable takes value strictly greater than 0, that means that the original linear program that I would like to solve isn't feasible. The original linear program that I would like to solve does not have any feasible solution. So I just say, hey, you gave me a linear program that doesn't have any feasible solutions. I cannot solve this linear program. I can stop. Okay. So this is the use of a phase-1 linear program. Even if you give me a very complicated linear program with a whole bunch of constraints, all kinds of negatives and positives and all kinds of crazy stuff, I can use this phase-1 linear program to find a feasible solution to the linear program that you give me, or to conclude that the linear program that you give me does not have any feasible solutions to it. Okay, good. So this is useful for finding a feasible solution to the linear program that you would like to solve. In the next iteration, we're going to see how we can start the simplex method with that feasible solution and then apply iterations of the simplex method to get to better and better and better, and eventually the optimal solution to the original linear program that we would like to solve. That's going to be our job for the next lecture. Okay, great. It's a good stopping point.